So hydrology is a fairly quantitative science, and one of the goals I have for the semester is to convince you that one of the ways to get better with applied mathematics is to understand dimensional analysis of the variables in your equation. And to introduce this topic, I'd like to talk about the dimensionality of the physical properties of water. So in terms of the basics of physics, if we're thinking about a bucket of water and we say something like water is matter, what does this mean? What does it mean for something to be matter? Well, it means that it has two characteristics. Water has mass and water occupies space. So that's easy enough conceptually, right? We have an idea of what mass is based on gravity. We can measure how much space the water takes up using various techniques. But how do we go about describing mass and volume objectively? In other words, when we try to put numbers on these things, how do we all understand what those numbers mean? Well, the first step is to understand the dimensionality of those variables. So we have a variable, maybe a lowercase m, that we could commonly use for mass. We say that water has mass. What is the dimension of mass? Well, a fundamental dimension happens to be mass. And we characterize dimensions with a capital letter, in this case a capital M, and we put it in square brackets. So this one's pretty straightforward. It's just a matter of mass being a fundamental dimension, and we say water has mass, therefore the dimensionality of that variable is m, or mass. We also say that water occupies a particular volume of space, and commonly a capital V might be a variable we use to talk about a volume of water. Well, it turns out you can work out what the dimensions of volume are, and they do break down into a simpler dimension than just volume. And let's work our way through the algebra to understand how this works. So if we've got a bucket of water that's roughly cylindrical, we can think about how to calculate the volume of a cylinder. And that's basically the area of the circle representing one side of the cylinder multiplied by the length of that cylinder. The dimensionality of an area then is going to be calculable by the dimensionality of the variables that you use to calculate that area. So just like units, you can carry dimensions through algebra and through calculations. So in this case, we want to know what the dimensionality of area is. We have to know the dimensionality of pi and r if we're going to use this equation pi r squared to calculate the area. So that leads us to something we can explore to maybe understand dimensions a little bit better. What are the dimensions of a variable like pi? Well, in order to answer that question, we have to know what pi is. So think for a minute, what is pi? Do you know the definition of pi? I'll give you a hint. It has something to do with a ratio that is related to the geometry of a circle. So the definition of pi is identically defined as the circumference of a circle divided by its diameter. So again, in order to come up with the dimensionality of pi, we have to know what the dimensionality of the circumference and the diameter are. Well, if we think about the diameter and we want to know the dimensions of that, the diameter is simply a distance, right? It's the distance through the center of the circle from one edge of the circle to the other. Now this distance, in terms of dimensionality, the fundamental dimension for a distance is what we call length, or a capital L. So if the diameter has a dimension of length, and that's the fundamental dimension, we can move on to circumference. It's a little bit trickier, but if you notice, circumference is curved, but it's still a length, right? It's a curved length, but it's still just a length. It's the length of that line that you could draw if you draw it around that circle. So both the circumference and the diameter are both lengths. If you let those lengths divide out, just like units would divide out in the algebra, you get a term where the two L's divide out to be 1 in square brackets. And this is how we indicate what we call a dimensionless number. It's a number where the dimensions will divide out, and you end up with a number that's a ratio that has no dimensions. So pi by itself is dimensionless. It's a dimensionless character of a circle, and it doesn't matter what size that circle is, that number is going to be the same. So if we go back to our bucket, we know that pi is dimensionless. How about that r variable? That's the radius of the circle, right? Well, the radius is just half the diameter, and you would think that has the same dimensionality as the diameter does. So that r is going to have dimensions of length as well. So as we work our way through all of this math, we can do the algebra simplified to say, okay, the dimensionality of an area is length squared. Now it turns out that you'll get this dimensionality no matter what shape you use for your prism. It could be square, in which case you have a length of two sides that you multiply by each other, you get length squared. So any equation that you have for an area is going to come out with dimensionality of length squared. Okay, so that gives us the area of one side of this cylinder. If we want to get the volume of the cylinder, we need to multiply by the depth or the length of that cylinder. Again, that's a length in terms of dimensionality. And ultimately, if we multiply the area times the length, we get a full dimensionality of length cubed to give us the dimensions of a given volume. Okay, so for the basic physical properties of water, having mass and having volume, we have dimensionality of those variables of a mass, or m, and a length cubed, or L cubed.